Yeah, cool.
I've never been.
All right, so it's a little after 4, so let's get going since it is a Friday. It is my pleasure to introduce Chen Li. Today, a little bit about his background. He's got a BS from Peking U and a PhD from Georgia Tech. Subsequent to that, did a postdoc in integrated biology and robotics at UC Berkeley as a Miller Fellow. I think the most important thing I want to emphasize, because these are not trivial things, associate professor. He very recently got promoted to associate professor with tenure. So that's why he's smiling. It's happy. He's happy to see us. It's because he got promoted. So, which is great. Got promoted in the mechanical engineering department on the Homewood campus here. He's got 3 early career awards, 7 paper awards by him and his students, and then 7 award finalists in biology and robotics conferences. What I really like about his research, and again, I hope that you guys had a chance to read some of his PDFs, is I think the really cool stuff happens at the interfaces between different fields. And he's someone that really does that. If you look at his website, it says, he wants to develop an approach called Terradynamics, looking at the interface of biology, robotics, and physics. Those things are all really cool to me. And in that world, you can basically do what you want. And I think he is a sort of a thought person when it comes to the concept of terradynamics. And that's a really important sort of new area. And so as someone that's a mechanical engineer that's thinking about biology and also in the way that this robotic design can be inspired by that, I think there's a lot for us to sort of get from that. And so I will leave it to Chen, and thanks for coming down.
Thank you, Matt. Thank you for the very kind introduction and invitations. Yeah, and I had great pleasure chatting with many of you here. So I'm going to give you a snapshot of the research that I have been doing since my PhD on terradynamics of animal and robots in complex terrain. So we have had the long history of entire fields of aero and hydrodynamics with many experimental tools and models to help us understand not only how animals move in fluids, but also create engineering devices that do so well. For terrestrial locomotion, we also have had a significant history of understanding how animals move on relatively simple, flat, solid ground. And the fundamental understanding of leg-ground interaction from these studies dated back to the last century had recently resulted in many robots that are moving really well on this kind of environment today. However, these models for terrestrial locomotion for a very long time have focused on understanding near steady state single mode locomotion, such as walking and running on flat rigid ground. And when it comes to more complex environments, such as desert sand or loose marching soil or forest floor and earthquake rubble, where you have many large obstacles cluttered together, then obviously these simple models will no longer work. And so, in other words, we need to begin to take a systematic approach by creating experimental tools and models to better understand how animals and robots move in this kind of environment. Yeah, so as a PhD student at Georgia Tech, I worked with Dan Goldman to study how legged animals and robots move on sand. We developed a device to control the compaction of sand so we can systematically vary the strength, much like a wind tunnel or flow channel, to control flow. Through these systematic animal and robot experiments, we can eventually develop models to make prediction. So I'm going to talk about a couple of these studies to give them an idea of my work there. Since my postdoc, I began thinking about how to study more complex 3D terrain where you have many obstacles highly cluttered together. And so that has driven, this theme has been driven much of my lab's works over the last 8 years. So we made quite a bit of progress on understanding how multi-legged animals and limbless animals make transitions between different gaits to traverse this kind of environment. And very often, these legged animals can also get flipped over. So we also study how they can ride themselves to an upright body posture. So I'll also give a very quick snapshot of some of these studies. So yeah, so the studies that I'll cover on both the locomotion on sand and in cluttered 3D terrain are going to be mainly focusing on those that involve the understanding of the role of morphology and design. We also made a lot of progress on understanding the behavior dynamics, control, and sensing, but I'm not going to talk much about this today. Towards the end, if I have a little time, I will show some very quick snapshots of some of the recent directions in the lab. And so first, so as Matt had already mentioned, through my training at this interface, we in my lab we integrate these approaches to try to develop tools and models to understand the terradynamics of locomotor environment interaction. So I won't, for the sake of time, I won't go into this. Yeah, so first on my PhD work on legged locomotion on sand. So I studied the silver-tailed lizard native to Southwest United States. Here's a video I found from YouTube to give you an idea how fast this animal runs. So you can see it disappears. Like of an eye. So this animal has been augmented to both in the lab and in the field to reach up to 50 body lengths per second, really fast, and it's able to do this over a diversity of environments ranging from very rigid to very loose sand. And so in the lab, we study these animals on two extremes: a completely solid surface, as you see here, as well as a granular surface sand, which you'll see later. So what we found here is that on sand, the animal only touches down the rigid ground with the very tip of his toes, and then the rest of the long toes bend into a C shape. That pushes the animal off. Here's a video of the animal running on sand. It's a little bit choppy, but what we found, the main difference is that the animal instead hits the surface with the entire foot with a level posture, making use of a large foot area to generate force. And then underneath the surface, we hypothesize that it's rotating backward and downward. Yeah, so here you can see the speed in the lab is not significantly different running on solid and granular surfaces, both reaching 20 body lengths per second. So from these observations, I did some simple modeling. So people have for a long time known that in large vertebrates, during walking and running, especially running, you can use your muscle tendon unit as an energy saving spring. Yeah, so here I have this hypothesis, even though I cannot, due to the instrumentation limitation, I cannot directly observe this. I can start from the kinematics to infer the muscle function. Yeah, so here you can track the points on the foot to then measure the foot curvature, which is 1 over the radius of this circle that you fit to the foot. So that's shown here, normalized. So initially it's straight, 0 curvature. During the stance phase here, when the foot touches the ground, you can see that the curvature increases and then decreases. And then during swing phase, it curves in the other direction. So yeah, so based on this simple observation, my collaborator Tanya Shea at Temple University, she did a dissection to reveal that under this lower leg muscles, you have this very long tendon, the equivalent of our Achilles tendon, which inserts to the very front of the foot. Yeah, so I can then use a very simple foot model based on understanding in larger vertebrates, assuming that the muscles are functioning as a strut, being activated much stiffer than the tendon. Then the tendon will be the main spring element. You can then, from geometry, calculate as the foot curves and then uncurves, how much the tendon length changes, as shown here in the stash curve. And you can clearly see that it lengthens and then shortens in the stance phase. So from this, we infer that the foot functions as a spring to help store and release elastic energy to make running more economical. Yeah, so we can further use this model to estimate that the level of energy storage, which is shown here. And you can see this is the total mechanical energy of the center of mass, which is reduced at mid-stance and then recovered, and that reduction happens to be about the same as the elastic energy storage. But not all the energy is stored will be returned. So to quantify that, you can then do this work loop experiment in an anesthetized animal to then see the resilience, how much energy is within the stool, which is basically lost. And then under this curve would be the energy recovery Yeah, so we found that the recovery percentage is roughly 40%. So from this, we can infer that if this much is stored, then 40% of it would be released, meaning that the animal can actually use this energy saving screen to recover about 40% of the energy that it would otherwise have to supply with its muscles. On sand, we know less. We can observe how its foot moves subsurface, but based on the above surface kinematics, we can infer that it likely goes through this foot rotation as well as penetration. And at this time, I did not yet have a force model developed to accurately calculate the force, but we have some very simple model. We know from the literature that when you move in sand, much like when you move in a fluid, the force generated by an intruder should be proportional to its area, perpendicular to the direction of movement. And then in sand, the deeper you go, the more force you get due to a hydrostatic-like pressure, much like the pressure in water. So the force you get should also be proportional to that. So from this very simple model, we should expect that during each stance phase, you should have a first increase and then decreasing ground reaction force, because your area is going to diminish as your depth reaches the maximum. Yeah, so at the very beginning, you have zero depth, a large area, but the force will be zero. Towards the end, as your foot has become vertical downward, its projected area pushing downward is zero. So even though you have a large depth, the force is still zero. So we should expect a force profile that looks like this, increasing and decreasing. Yeah, so from this simple assumption, we can then do a force balance. Sorry, what I'm talking about here is all vertical force only. We can then do a vertical force balance. Your average vertical force over a cycle should balance your body weight. Yeah, so that's what we did. Yeah, the area under these two curves, force from both hind foot together should balance the weight. We're ignoring the 4 feet because they're very small and don't penetrate much. So anyway, with this, we can estimate the magnitude of these forces, and when we integrate these acceleration from these forces, calculate the resulting speed, vertical speed, you can see they match the experiment fairly well. Yeah, later we also did X-ray observation to confirm this foot rotation hypothesis. Anyway, with this, we can also do an energy calculation. In sand, sand is different from a rigid ground in that on a rigid ground, you can push down and it will bounce back. But sand, as you displace it, it doesn't bounce back. So it's a plastic deformation. So that energy, that work that you do into the sand is permanently lost. And so we can use our estimated force profile to calculate the energy loss, which is also comparable to this energy reduction. So here, compared to the rigid ground, we can infer that the legs must do twice as much mechanical work to recover the mechanical energy of center mass. And we see some evidence of that. For example, when we measure the knee extension, the knee angle, we can see that on sand, the knee actually had to extend much larger angle compared to that on rigid ground, indicating it's doing more muscle work. Yeah, so I also did several robot studies. Eventually, towards the end of my PhD, I wanted to have a force model to help us accurately predict ground reaction forces on sand. Yeah, so here the key insight is from both animal and robot work. You can see that they have a foot or leg that might have a complex shape, which moves along a complex trajectory in sand. So if you look at each little segment of a foot or a leg, they might each of them might be moving at its specific movement direction at its specific speed. Also, it has a different specific depth as well as orientation. Yeah, so we came up with the idea that if you can use a simple plate element and try and push this plate into sand at different orientation, different movement direction, reaching different depth and at different speeds, then perhaps you can calculate the stress, the vertical and horizontal stress, basically force, lift, and drag force divided by the area. And you can integrate those stress over the surface of a foot or leg on the leading edge to then calculate the total force. And you might think this might be trivial, but it's actually not. If you do this for fluids, locomotion in fluids at a higher Reynolds number doesn't work because of the complex dissipated flow. So it turns out that this idea had already been applied to model low Reynolds number fluid in which the forces are dominated by viscosity. So we don't know whether this will work for a complex media like sand, but we decided to try it anyway. So as I mentioned, there are these parameters, depth, orientation, and direction, which are different for each element. Speed is also different, but turns out in sand, because the forces are dominated by friction, the forces are actually insensitive to speed, unless you reach really high speed. In our case, it's not relevant. So we then did these experiments to measure force, lift and drag force on the plate element as a function of these three parameters. And well, what we first found is that, as I already mentioned, there's a hydrostatic-like pressure. So the force is always proportional to the area and the depth. So we can now define a coefficient, if you will, a lift or drag coefficient, which is the measured lift or drag force divided by the area of the plate divided by depth. And that's plotted here. So this is just one particular case. I did experiments to vary the orientation and the movement direction to map out this lift and the drag coefficient as defined as a function of these two angles. I'm only showing the lift coefficient here for simplicity. So now with this, we can then see how well we can predict the force. So we rotated a simple C-shaped robot leg into sand and measured the force profile as a function of this angle of the leg. And then when we integrate this without any model fitting parameters, you can see it matched really well. This turned out to be more accurate than the lower number fluid case. And that's also a quite good match for the total drag. So now we verify this works well on a single robot leg. We want to further see if we can predict the locomotive dynamics of a robot. So here, I used a little toy robot with these C legs and 3D printed legs of different curvatures. This is a C leg in the forward direction. So on top is the experiment, and here is the simulation. You can see the legs are broken, and even the body penetrating the surface are broken into little elements. You can then figure out the force coefficient and then figure out the force sum them together to calculate the dynamics. So here is the speed as a function of time. And it worked really well for all kinds of leg curvature. Here is the same leg shape but reversed in this direction. And the robot moves much more slowly, but the model still predicts well. So over a very large parameter space, we vary both the frequency as a parameter for kinematics, as well as the curvature as a parameter for morphology. We can see there's a very good match between the model prediction and the experiment. So this gives us and because this is a very simple integration, it takes time to do experiment, but once you have basically these force coefficients, when you do integration, it's very fast. So we can do very quick optimal design for robot, for example, figuring out the best curvature running at 4 hertz. So that's my PhD work. And then as I moved into to Berkeley, I began thinking about studying how animals and robots go through these highly cluttered environments. And here you can see these animals are doing very well, and especially the cockroach on top. You can see it's making transitions across many different locomotive modes, not just stabilizing its body for walking around. And there have been actually a lot of studies or robots developed to move in this kind of environment. This is the robot you saw earlier. It's called Rex from Dan Kotichek's group. And you can see this robot actually does quite well. This was back in 2000. So this robot is basically inspired from a cockroach. What it does is it kept throwing its legs forward. It doesn't have any, back then, it doesn't have any sensing or feedback control. Basically, its design, its body plan, and its leg viscoelastic properties are just so well tuned, inspired by a cockroach study from Bob Pohl's lab, that it already solves much of this problem. However, we still lack a fundamental principle understanding of interaction with this kind of obstacles to actually control and generate the desired locomotive condition. So that has been and I was also really inspired back then when I saw this video from Dan Phototek's group, where they put this robot through a FEMA simulated earthquake rubble, and it kept failing, but getting stuck against obstacles and flipping over. Yeah, so that motivated much of the study. Yeah, so in Bob's lab, we have cockroaches. So I studied this white cockroach from Central America, where they had to overcome cluttered, dense vegetation all the time, even leaf litter. But when you look at this kind of terrain, it seems formidable to begin to understand. So back then, I started with something a bit simpler, which are grass, but even real grass can be highly variable from blade to blade, or from species to species. So again, much like building a wind tunnel, I made these laser cut paper grass assembled so I can do repeatable experiments. So here's a video of these cockroaches running through. You can see in this trial, which took 4 seconds, the animal tried to push through a couple of layers, climbed up, and then fell with the beams. Yeah, so I then observed each trial to write down the locomotor mode transition. And here's another trial, in which the animal is much more effective. It only took 1.5 seconds. What the animal does is, as it pushes against the beam, it very quickly transitions from pushing to rolling into and through the gap to traverse, which is much more quicker. And yeah, so these are the two trials you saw earlier. And once you take many trials, you can get these kind of probabilistic locomotive transition diagrams. So the numbers and the thickness of the arrows indicate out of 100 trials, when you start 100 trials, how many of them go through each of these transitions. So you can see it's highly stochastic. When you look at each trial, it seems unpredictable what the animal will do. But when you have a large data, you can start to see the trend. Here, the main trend is that the animal uses this rolling mode most frequently, about 2/3 of the time, to eventually traverse. And that, when I measure the traversal time, that also turns out to be fastest. If the animal ever uses any of these other modes, it takes on average 4 seconds, whereas on average for rolling, it only takes 2 seconds.
Hey, Chuck, out of curiosity, how did you motivate the cockroach to go through the obstacles?
Yeah, so this is figured out by Bob's previous students. So you use a little brush, or just like a little rod with something soft at the end, and you hope them to have these little kind of spines that can sense mechanical signal, and that get them scared. And also we put a little like a little egg crate on the further end, which is dark, so that as they move through, they will hide in there. Yeah, so I also have a co-advisor, Ron Fury, who's a roboticist, and his lab had developed these robots similar to the one you saw earlier. These are much smaller. These are palm-sized robots. Computer is a little old. Yeah, so these are the robots from my advisor Ron Fury's lab, and you can. At the time, it was the fastest running robot in terms of body length, reaching 20 body length on flat ground. But you can see here, even when the gap is wider than the robot body, because of this highly unsteady and oscillatory movement, it tends to hit some part on the obstacle and will actually get attracted towards the obstacle. That greatly reduces its traversal probability. Yeah, so what made the animal so much better? So one obvious difference is the body shape. You can see the animal have this well-rounded shape. It actually resembles, if you take an American football and cut it in slice, it resembles that shape. Whereas this robot and many of our existing robots, they have these highly rectangular shapes. Yeah, so I was inspired by the streamlined shape compared to a blunt body shape, reducing drag in fluids. So I hypothesized that maybe this shape can help them reduce the resistance and attract them towards the gap. Yeah, so to test this, I gave my cockroaches little backpacks. I had backpacks of various shapes, basically gradually reducing the curvature here. This shape looks like the animal shape. This is the kind of intermediate control. It has similar mass to these other ones and similar friction properties. This is a 2D oval, and this here is a 2D rectangle. And you can see this gradual reduction in the curvature has significantly reduced the animal's ability to make transition to this most effective rolling mode. Yeah, so inspired from this, we then added a very simple shell without any changes in the robot. The robot, again, is blind. It just runs forward, throws its legs, moves forward. But this mechanical interaction leads the robot to roll its body, traverse at high probability. But that comes at a cost. Sometimes the robot will roll too much, and here then it's stuck. There's nothing it can do because this shape is stable upside down. Yeah. So in my animal experiments, I also observed that sometimes they will also flip over, but they always very quickly right themselves. Sorry, I don't know. Yeah, I think over zoom somehow it becomes choppy. So the animals, they what you didn't see clearly is they would very often open their wings to push against the ground to do a somersault. Yeah, so that led to a very simple robot design, cutting the shell in half, but to push against the ground as wing. But this got me interested in self-riding. Yeah, so I worked with undergrads, master student to study 3 species of cockroaches self-riding on a flat ground. Here are some representative trials. You can see, depending on the species, they have different strategies. The American and the discoid cockroaches both can use wings and legs, whereas the Madagascar cockroach changes its body shape to roll over. You can see they can do this very fast, but actually very often they really struggle. They have to do this many, many times, keep doing the same strategy or switch between a couple of strategies many times to succeed. So this self-riding is actually highly strenuous. And so at this time, I started thinking about, and I developed this very simple physics model to understand this. Yeah, so here, I decided to focus on this discoid cockroach riding using wings. So if you push really hard with your wings, you can do this somersault much like that robot. But what the animal often does is it is not able to do that. It's not able to push hard enough to do a full somersault. And you can see it just raises its body in the air, but not able to fully complete the full pitching. It keeps struggling. Yeah, and this is because if you look closely, the animal has this head that sticks out, even though you have 2 wings that you have that tries to push against the ground. This head it gets in the way. It's like you have a triangular support that you can't generate enough energy to pitch over this wing, and you're constantly stuck in that metastable state. So because of that, what the animal ends up doing when they do self-ride, they do succeed, is they always start to roll to one side or the other, as you see here, illustrated by this diagram here. And what's really interesting is if you look at this video above again, you can see the animal is always throwing its legs around, flailing it around. And so this is reminiscent of a very simple physics problem when you have a little particle trapped in the potential energy well. If you have a little bit of kinetic energy or thermal fluctuation, will give you, when that fluctuation becomes comparable to the barrier, it'll give you a probability of traversal. And the closer that energy is to the barrier, the higher the chance you can escape attraction to that basin. Yeah. So also I saw this paper by actually 2 applied mathematicians trying to understand turtle self-riding. So basically, when you consider self-riding, it basically requires you to raise your center of mass to overcome a potential energy barrier. You have to first raise it to reach this highest point, and then you can fall under gravity. And so overcoming potential energy barrier is the most important challenge here. And then they found that when you have, for certain turtles that have these really flat shells, they have to overcome a very high energy barrier. So they seem to have evolved really long muscular necks and limbs to help them generate large torques and input energy to do this. There are also other turtles that have evolved shells that are highly domed with a low center of gravity. So when you flip over, it's already unstable. It will that's basically this gravity is going to do most of the job, but it does get stuck sometimes because you see these little kind of concave surfaces, so it does get trapped in local energy minima, local basin, and in that case, the animal starts to wiggle, to bob its head and limbs to use a little bit of kinetic energy to help it get out of those barriers. And so we think perhaps the cockroach, like flaming, is doing this. Yeah, so to test this hypothesis, my PhD student Martin built a robot because it turned out to be really hard to do a full 3D construction of the movement with occlusion and the constant rotation of the body. The robot can measure this relatively easily. We can also systematically vary the parameters such as how much the wings open and how much the legs flare. Yeah, so here are some representative trials. Here is the robot on the left without any leg flailing. It just tries to open the wings, and we specifically designed this big head so that the barrier is large, so the wings can help it to get over. But now, if you start flailing this little simple leg around, then you start to roll either to one side or to the other very quickly out of being stuck. And with the robot, as I mentioned, we can fully reconstruct the 3D motion. We can actually calculate the potential energy landscape. So initially you see there's this deep basin here. That's when the wings are not open. When it's basically when you have a spherical shape. Like a ellipsoid shape. When you pitch or roll, it's going to raise your center of gravity, so you have a global minima there, like with zero roll and zero pitch. And then when the wings start to open, you can see this potential energy landscape start to evolve. Specifically, you see this. Sorry, it's quite choppy, but you see this basin starts to shrink and move towards this line, which is the highest barrier. Basically, that somersault. This is 90-degree pitch. You have to pitch over to 90 degrees to reach this highest barrier. And as you open your wings, you're trying to approach this, but you can't quite do it. And this global basin shrinks to a local basin, but it's still attracting you towards it. So that's that three-point triangular contact. That's that stable state. You're almost getting over this barrier, but not quite, and you're stuck in there. So you kept pitching out, pitching back down, pitching out, pitching back down, without any lateral perturbation. But now when we add some lateral perturbation, you can see it starts to throw you off course from this pure pitching, and very quickly you actually, even though you can't overcome this barrier, you very quickly find a path to reach this these two minima, which are the upright state. So that's upside down, that's upright. And so our very simple modeling here confirmed our hypothesis and explain why the animal display this highly stereotypical movement. Yes, so here are many trials overlaid together. Oh yeah, and we have further quantify the barrier. So here we measure the barrier if you try to do a pure pitch, and the barrier if you try to do a pure roll, which are shown here, and both of them are going to change as you keep opening and closing your wings. And what's most important here is we find that as you keep opening your wings, both of these barriers are going to reduce. But the roll barrier, because initially lower, is going to come down more quickly than the pitch barrier. And this is the kinetic energy that we measure in the system. So you can see, if you try to do it in the pitch direction, your kinetic energy won't be able to overcome the barrier until the wing opens to 90 degrees. However, in the rolling direction, as you open your wings, it reduces your barrier so that even at 70 degrees of wing pitch, you already have enough roll kinetic energy to throw you to the side. Yeah, so wing opening alone is not sufficient, but it allows the leg perturbation to overcome this lower barrier. So the cooperation of these two types of appendage movement is crucial. Okay, so so next I'll talk about some of our snake locomotion work. So snakes, as we all know, they live in nature. They can move through all kinds of environment. Here you can see some videos of snakes going through highly 3D terrain. But ironically, it's very similar to leg locomotion. For decades, our studies of snake locomotion using various skates have been mostly on flat surfaces. Yeah, so there, so we thought there might be environments such as these where you have large obstacles that the snakes have to overcome, but there are not enough points that they can wrap their body around to use as anchor points. So a very large, smooth obstacles. So to study this, we use the variable king snake, and we built a very simple step-like obstacle with variable height. We also applied two different surface, different friction, high and low friction. So here you can see on a high friction, high step, the snake initially does this lateral body bending and then does this cantilevering behavior, basically keeping its body straight in the air and until it reaches the top surface, which then goes back to lateral slithering. You can especially see this from the front view. You have this this cantilevering body segment basically moving in a vertical plane. Oh yeah, and then we developed a method from a few markers to reconstruct the majority of the body and estimate the center of gravity position. And we found that it always projects within this ground base of support, which means it's stable. And when we vary the friction and the step height, you can see it becomes much more challenging, especially in this case, the animal slips much more when the surface is low friction, and it seems to be pushing its neck downward here to try to hook onto the top surface. So it took much longer to traverse, but when we analyze, the stability is still always stable. So based on this very simple gate, transitioning from lateral bending to cantilevering back to lateral bending, we then build a robot to implement this gate. And here you can see this is in real time, not sped up. You can see the robot moves pretty fast, traversing this pretty significant step at a very high probability. Yeah, so even though we use the robot but that's not to say there's no problem. When we challenge the robot with a much higher step, you can see it starts to struggle, it starts to wobble back and forth, and eventually falling over. So the probability of traversal is much reduced. Yeah, so again, we wanted to see what can we do to improve the robot. So you can see many differences. The snake body is much more continuous. They have 200 plus vertebrae. Our robots only have 20 segments. Yeah, so that's one thing. And the sensory feedback control, as I've already mentioned. But one very simple thing that might help is the passive compliance of the body. You can see our robot has these wheels that are rigidly attached to the motors. Yeah, so to test this idea, my student Shiva added a very simple car-like suspension, and without changing anything else, it recovers from that failure mode quite well. So that increased the traversal probability. And this we didn't specifically aim to achieve this, but it turns out our robot's performance is actually quite good and much better than most previous snake robots. So here is a graph showing the step height normalized to the body length, plotted as a function of the time per traversal. And here are all the previous robots except one over there. And if you draw a line that starts from the origin and going through your data, then the slope of that line would be your normalized traversal speed, which is the step height divided by traversal time. Yeah, so you can see that our robot achieved both rigid and compliant, especially compliant with higher probability, achieved higher speed than most of these previous robots. And we think that's because these previous robots, they do not learn from animals. They use these highly artificial gait, which do not consider this requirement for stability. So the robots are moving relatively slowly. Yeah. So the last few snapshots of recent work. So after my PhD, I focused on studying something that's not similar to SEN, just to kind of show my independence from my PhD work. But recently, I began thinking more about these kind of flowable substrates. Yeah, so from literature review, there's a significant difference in the mechanics and flow rheology between sand and mud. So sand is basically solid water mixture where you have most solid consisting of coarse grain, about 1 millimeter plus. Whereas when you go down to dozens of microns or even smaller particles, and they are mixed with water. They have a lot of cohesion. When you have sand mixed with water, you have a little bit of cohesion from surface tension, but much less strongly. Yeah, so the mechanics and presumably the locomotive strategies moving on sand and mud is going to be really different. And despite a lot of studies, observational studies of animals moving on mud, there hasn't been much, again, understanding the mechanical interaction. Yeah, so recently my lab developed ways to, again, precisely mix clay with water at these ratios and keep the water level relatively constant over a significant time, so we can study animals. Yeah, so we have been looking at amphibious fishes that live at the land-water interface. We studied mud skipper, which use this crushing gait, mostly using fins to prop its body up and propel it forward. The rollfish is a bit like a snake, using mostly lateral bending. And then the bishir combines both lateral bending and the fin to try to raise the body. Yeah, so we've been studying these as model organisms to look at these three main strategies, which covers most of the amphibious fishes. And we do have some really interesting observation that previous studies haven't found. Specifically, we found that most of them seem to, when the mud becomes really challenging, they seem to start to want to move out of the plane. You can see here the mud skipper is using its tails to thrust itself upward. And then the rollfish here is lifting. Yeah, you can't really see due to the, here. There's significant lifting. So all the previous fish locomotion studies, mostly on swimming, have really not observed much vertical body bending, but we think this might be a novel strategy for challenging terrestrial environment. Yeah, this is actually a bit like snakes. Snakes also, when they are encountering surfaces with friction that's too low or too high, they're going to selectively lift part of the body to modulate ground reaction forces. Yeah, so we're also been developing a robot here as a 3-in-1 robot, which can change its gait, lift its fins to kind of mimic these three different model organisms. And we're also recently adding motors to lift the body. Another recent direction. This is a collaboration with Andrew Bordas in biology here. So his lab you've probably seen his lab have been studying how spiders build webs. Very, very nice kind of behavioral quantification and modeling. But he reached out to me at the beginning of the pandemic and wanted to study this vibration sensing. Yeah, so one really interesting behavior that biologists have wondered for decades, and he also became interested, is this. You see this dynamic crouching of the spider. They kept actively moving their legs to move up and down when the prey is dropped. Yeah, so the challenge here is that in a biological system, it's impossible to measure all the vibrations throughout the system, because the techniques that are developed sensitive enough to measure it can only measure at a single point. So you can't really, if you don't have a spider or a behaving spider or a prey, you can keep sweeping this web. But when you have a behaving spider which keeps moving around and even wraps the prey and just kind of damaging its own web, and then every night it's going to tear down its web and make another one. So it's just impossible to collect systematic data to understand the principle. Yeah. So my student Eugene. Oh yeah, here there's evidence from a recent modeling study which showed that observed that black widow spiders they build cobwebs, not these orb webs, but they found that when the spider is in different behavioral states, for example, when they're really hungry, when they want to eat, or when they're ready to mate, or when they don't want to eat or mate, they assume different posture. So they hypothesized perhaps this is a adjustable mechanical filter, because the vibration have to pass from some external source, such as a prey or a potential mate, through the web, and then up the joints, the legs, to be sensed by the sensors on the joints. So basically you have a mechanical filter that you can change by changing your body posture. Yeah. So my student Eugene built a robotic system to study this, so that we can measure vibrations everywhere. We have a prey robot that shakes, spider robot that can change and do this dynamic body posture, leg posture, and we can also control and measure the tension and track all these points to measure the vibration of the entire web. Well, we have some accelerometers on the legs to measure the joint vibration. Yeah, so here are just some very initial results. We found initial evidence that when the spider does this crouching, it seems to allow itself to detect whether there is a prey robot, how far it is. Here you can see the vibration. This is after the Fourier transform in the frequency domain. The vibration has a peak here when there's no prey. So basically, what the spider robot does, much like the real spider, they do this up and down, and then they stop for a while they generate some self-induced vibration, which then they can sense. But then if you do have a prey, then you get a very different profile. And also depending on where that prey is, this is when the prey is very close. If you move the prey very far, then that signal approaches this one. So it's very preliminary, but we think this is initial evidence. I think that's something. At the end, this is not my work, but I want to show this, especially given the audience here. I feel there are opportunities to use robots as a tool to study the role of functional morphology together with behavior in both extant and even extinct animals. This is from Alke Ishberg group in collaboration with John Nakatura, who I think is a paleontologist. Yeah, so they built this kind of fossil-based robot with, so here, that's the robot. They can then use this robot to add the behavioral component. You not only have these morphology from fossils, but also you can change the kinematics, the gait, range of motion, and perhaps even material properties might constrain from material. What's not shown here is they can also match the gait, the footprint to match the fossil footprint, and eventually, based on those validations, they can then sweep parameters to basically generate this performance landscape of forgot what metric, but they can come up with some score, some performance score, much like a fitness landscape for locomotion. And they can compare the optimal gait for this little fossil robot with a bunch of extant animals, and found that it's more similar to, I think, a caiman crocodile. Yeah, so I'd be excited to discuss this kind of collaboration among others. Yeah, I would like to thank all my advisors, collaborators, and all the amazing students who have done all the work. Of course, our funding sources. Thank you, and quick question. Yes.
You had a slide that showed 4 gates in snakes.
Oh, yeah.
What determines snake gait? Like, when do snakes transition between those 4 gates, or is it like if you're a sidewinder, you're a sidewinder, and that's the only gate you use?
Yeah. So I only know a little bit about this. My collaborator Henry Astley, who taught us to run all the snake experiments, he would know this really well. But I think sidewinding is very specific to only a few, like 8 species of snakes living in the desert. So this one is very specialized. And then this is the most widely used lateral undulation. And then the concertina is also quite widely used, but usually when it becomes more challenging, for example, here in this video, what happens is you can see it actually looks somewhat like lateral undulation, but sorry about the choppiness, but what the animal does is it places down part of the body and just use friction to stay there as an anchor point, and then lift other parts of the body to move forward. And they also do this when they're in very narrow tunnels. They are going to use part of the body to brace against the wall and then pull or push the other parts. So this is a very intermittent movement, and this is much more costly. So from what I learned from Harry, they usually only do this when they cannot effectively use lateral undulation. And this one actually, again, don't quote me on this, but I think this one is more often found in the very big snake, like python, like boa, like and this one is very energetically costly. But this allows them to move even without any room to bend the body. What they are doing is what's really I was really surprised when Henry told me that people when they use X-ray to look, they don't see the backbone and the ribs moving much at all. It's mostly just the muscles that are pulling the skin move relative to the skeleton inside. But it's a bit like an inchworm.
Yeah, so these are less like gaits, like where you think of like a horse could have a trot and a gallop.
Oh, yeah,
transition between those.
Yeah.
Humans have walk and run. These are more like
Yes.
species or group specific adaptations. Like
I guess you can, in that sense, yes. Yeah, but also I think this when I get more time, I'll try to update my slides and my class. I teach all this in my class, but I think this is a very incomplete view. Like Bruce Jane, who was Henry Astley's like a master's advisor who have studied things for decades. He has recently a paper. He proposes many different variation of gaits. Yes.
So early on, you showed a robot where basically, if you're looking at the left side, the left front leg moves forward at the same time as the left hind leg moves forward. Some animals locomote like that are quadrupedal, but the left one goes forward while the right one's going back. And again, sometimes that varies with speed. Have you guys looked at that at all in your robots?
Are you talking about this one? Or?
It was even before that, but on some level, it doesn't make a difference. I'm just kind of curious if all your robots, it's like both left go forward and then both right go forward, or it's like they alternate.
Yeah. So we haven't focused on that a lot. There is one study I can. So maybe first a little bit of context. So this robot I showed earlier. Yeah. Again, sorry for all the very choppy videos over the Zoom, but this is inspired from a cockroach. So this uses an alternating tripod gait. So you have front and hind on one side and mid on the other side. They're always in sync, and then the other three are in sync. So you have always a tripod hitting.
Oh, okay. Yeah.
So most of the six-legged robots use this gait.
Okay.
Even the one you saw later, the small one, getting stuck against these like fake grass. But you might have seen them. They seem to start moving in synchrony. That's actually like undesired. That's because for that robot has both these. So that robot has just one motor, which through a clever transmission mechanism they designed moves all six legs in this alternating tripod fashion. But because it's built from cardboard, that their goal is to make a robot that's very cheap. And eventually they even had a spin-off little toy company called Back Robotics. But it's made from all these various cardboards often, so there's quite a bit of give. So when it's hitting against the obstacle, the legs start to synchronize. But then going out of phase. So it's but we do have one study. So the leg coordination we haven't studied very much, but there's one study recently that's not really on the leg coordination, but can give you a flavor of the importance of that. So here, so I showed the cockroach going through this transition from pushing against flatter obstacle to rolling in. So one of my PhD students had looked at that carefully. So he had these markers and these spheres, these points to track the body and the legs. It took a lot of effort because with the occlusion, he just doesn't track it very well, even with deep lab cut. But he eventually got a lot of data to show that the animals are doing several things that must involve some active adjustment. So first, when they're pushing against the obstacle before they roll, their legs are really sprawled out, so presumably to prevent them from falling, to have that stability. But as they start to roll, they are going to tuck the legs in to make it less stable, so they can more easily roll in. And then in that process, also one leg will, depending on which direction you roll, one will push and one seems to be pulling. So presumably generating a torque. And there are two really interesting things. If you look from the top, as they wedge into these little gaps, their abdomens start to bend quite a bit. So we think that that's because if you look there, even though their body is mostly smooth, there are these little edges and corners which get stuck on the edges and corners. So maybe that little perturbation helps them become unstuck. And finally, this one we still don't understand. They have this neck joint that as they push, they kept bending the neck up and down. So we had different hypotheses. One is that perhaps this is like a form of active sensing. So a lot of, almost all sensory modality people have found, like if you move your sensor, it helps you improve your sensing through various mechanisms. But we thought here that's really plausible because we think that what the animal is likely sensing is the resistance, and somehow adjust its movement to reduce that resistance. We have a potential energy model, landscape modeling that I don't have time to talk about, but basically we have a physics model that allows us, much like that self-writing potential energy landscape model. We did a similar modeling to show that the animals are hopping from one basin to another basin. This start in this pushing mode is one basin. You are attracted to that basin, but if you want to go to this easier mode, you have to overcome a barrier to reach another basin on that landscape. So how do you sense this barrier? You can't use vision because this is a physical interaction. So we think it's likely the force, the resistance that the animal are feeling, which give you an idea of the potential energy landscape. Because a potential energy landscape, if you take a gradient, that's going to give you the conservative forces. So we actually recently did experiments to show that by feeling the forces, actually not in an animal, in a robot, we had these force and torque sensors to show that we can actually reconstruct that landscape. Yeah, sorry, but here, what I'm trying to explain is that because you don't have a long range sensing modality to sense this interaction, you have to feel it, and you can only feel it at any moment. You are only in a single state. Like here, I have this body posture. I'm feeling a large resistance. The next moment, maybe I change my body posture. Maybe that resistance changes a bit. But you have to keep changing, moving yourself to be able to sense around some neighborhood. Or if I move this way, that resistance is increasing or decreasing. So we think this head maybe, or together with even the body oscillation, might be helping you explore around your current state to know to which direction is better. Yeah. So.
Was there any evidence that the cockroaches got better?
Learning?
Yeah.
We never. I thought about this a bit when I was at Berkeley. Bob suggested me to collaborate with Lucia Jacobs, who she's mostly spatial learning, like squirrels, where they hunt, they hide their food, etc. So I tried to do it, but I just know too little, and I think the collaboration was a bit too loose, so it never got going. But from the very little I did, I don't see any evidence. Yeah.
So how well do these legged robots perform relative to just robots with wheels? And like, do you think there'll come a day where we'll be sending legged rovers to Mars or something?
Yeah, that's a great question. Yeah. So it depends if it's flat ground with high traction, then wheels is the king. There's just no. Okay. It's so efficient and so reliable, and also so easy to make and maintain. So I think that's why even there have been so many attempts to develop non-wheeled systems, or even there are these what's called wheels on the leg or legs on the wheel, right? So for example, you have wheels, but then on top of it you have a leg, you can raise the wheel. But none of these have actually been sent to Mars. I think that's probably just because NASA they are so conservative, they want something reliable. I've even learned, I was really surprised when I talked with the experts who have worked with NASA. Even with the latest mission, they're using computers that are like 40 years old because those are proven to work. Yeah. The challenge is that for wheels a lot, where you have things like sand or large obstacles, then it can do a lot. Right. But I would say, I think there's still a long way to go for bio-inspired robot to really become very, very robust. Like you see, there are all these amazing videos of Boston Dynamics robots, like even doing somersault, like a humanoid robot, and these quadrupeds. And then there are many universities who are these days applying deep reinforcement learning to train the robot to stabilize, like on a mountain, like going over streams, etc. But a lot of it is like a Boston Dynamics. They will never publicize this, but if you talk with them or even people who have worked with them, like to generate each of those amazing videos, they have to do it many, many times. They have to fine tune the position of this little box, etc., like fine tune the controller. So it's just very far from being robust. And the learning approaches, I think I think there's certainly usefulness, but I'm certainly biased from my I guess physics kind of mindset, but also my training with Bob Full, the biologist, that I think that to really like operate well in the real world, having to do many tasks, it's the whole package. You can't just rely on one approach of learning, of trying to optimize to have some, just like learning to play a game. You're optimizing one thing, but there are just so many, like people these days, they get a robot that they buy from a company, and the robot is far away from the right hardware platform for a certain task, and they train them to demonstrate some very mediocre performance. Even my postdoc advisor, Ron Fearing, was complaining that he has junior colleagues at Berkeley, who does that, trying to train some crappy soft robot to grasp some object with performance much worse than his PhD work 50 years ago. And they were claiming theirs is always the best and can solve everything. So that's unfortunately, I think we have to wait till this hype to go. Yes.
There seems like be a wide range of like size of the robots. Like, is there like an optimum size? Like, how does the size overall? Because like, if you would just double, like thinking of the sand robot, if you would just double the size, the volume would cube, and the surface area is the key. Like, you would have, it wouldn't just be a doubling of the feet length in the surface area because it'd be not linear. Is there like optimum size that you use, or do you test different size robots?
That's a great question. So specifically for sand, I don't have a slide here, but one of the students after me, like overlapped with her, and I did some initial work. But Fei Chen, she's now a professor at University of Southern California. She actually much of the data is from my advisor Ben Coleman, but she followed up on some modeling and robot work. But they have shown, and as you can maybe expect a bit from what I have shown, here it's really it's not just the absolute force. Like if you have a large foot, then that distributes force that gives you a low pressure, so you sink less deeply. So basically, there's this hydrostatic-like pressure in sand that the deeper you go, the more force you get. So that's in general true. But if you have this for the same body weight, if you have a much larger foot, then you won't sink as much. So on sand, the big challenge is the sinkage. When you sink more, then your step cannot be as long, and you also get drag. So basically, her study have shown that comparing across several lizards and crabs, as well as a robot, they don't really differ very much in size, but they differ significantly in their weight divided by foot area. Basically, that pressure applied on the surface, and that seems to be a good, like a predictor of the performance. But I'm not an expert on scaling, but there have been, for example, terrestrial locomotion on rigid ground. There have been many people like Andy Buehner, for example, throughout his early career, he has done a lot of scale, kind of mechanical modeling to try to understand the consequence of scale, and others who develop those like spring-like bounce, center of mass bouncing dynamics. They also thought quite a bit about scale.
Thank you.
Yes.
Hey, Chen, just out of curiosity, what's your thought on that giant sandworm in the movie Dune? Is it pure fantasy, or those things are scientifically possible? The giant sandworm in the movie Dune?
I haven't seen
Dune 1 and Dune 2.
I haven't seen that, but sorry, the question is, do you think those are feasible?
Yeah, scientifically even feasible, or just pure fantasy?
So what do they do? They just crawl on the surface?
No, they go down. Yes.
Yeah.
down and up and yeah.
Oh, so yeah, so a couple of thoughts. So one thing is, yeah, actually, like burrowing into sand. I think we like my PhD advisor Dan Goldman had done some work like, of the sandfish lizard, and also snake burrowing in. They have understood like how the bending gait as well as the morphology specifically like these burrowing lizards, they have a nose that point downward. So that turns out to be critical that when you drive an object, if it has this curvature when you drive forward, it gives you a force that keeps you subsurface. If it's basically you have to break the symmetry to point downward. If it points forward or upward, it gives you a force that you will come up. So I think on the robot side, I've seen people trying to develop robots to burrow, but I think they're cheating a bit. I've seen the latest that they claim it's the first like limbed robot that can burrow from Hannah Seward's group at Berkeley. I think it's very nice engineering development, but they cheated in using like plastic particles that have a density quite a bit lower than the robot. So the wave itself helps it going. So I think it's actually, I haven't thought very much, but I think it's somewhat amazing that animals did, because I could be wrong, but I think from the scaling study I've seen, we can typically make a good approximations of animal effective body density similar to that of water, not too far away. So, but the density of soil, sand, or mud typically is like 3 times more that of water. So I think animals must be doing something really good, like combining their morphology and I don't think people have studied that carefully. But I think that would be, if I would say that would be a major challenge to just be able to go in, because as I mentioned, the deeper you go, the higher the pressure. That your weight is only going to do so much, getting you to go a little bit of subsurface.
If you have time, watch the movie. It's the best sci-fi movie I watched.
Well, if there are no more questions, thanks again, Chen, for.
Thank you very much.